Hello class, this is CSE-5250, section 61, week 10, technically week 11, fall 2024. So, with pthreads under our belts, I'd like for us to start looking at OpenMP. So what is OpenMP? So, that is yet another library that we can use to write multi-threaded programs. But unlike pthreads, OpenMP has a lot of conveniences that we can use. Basically, if pthreads is a lower level means of writing multi-threaded programs, OpenMP is a higher level means of writing multi-threaded programs. So, OpenMP, it's an API for writing shared memory parallel programs. OpenMP makes it easier to write parallel programs. OpenMP allows the compiler and runtime system to determine the behavior of threads, making it easier, compared to pthreads, to program. So, the idea behind the development of OpenMP is this. It was developed by programmers who believed that writing large-scale, high-performance programs using other APIs was too difficult. So basically, back when we were using pthreads, we found that we had to do several things just to get a thread to run. So for example, we had to allocate memory for a thread handle, and then we had to pass that thread handle and a thread function into some other function before we can for the program to even fork into another thread. And then when that thread is done executing, we gotta call join. And if we forget to call join for some threads, we're gonna probably get, for example, zombie threads. And it's gonna just waste system resources that way. Basically, what we're doing with OpenMP is we are extracting away a lot of those nitty-gritty details associated with pthreads, making it easier for us to write multi-threaded programs. So say goodbye to allocating memory for thread handles. Say goodbye to calling fork and join. So now, for us to get started, let's get started with a simple Hello World program. And with that, I actually have a few Hello World programs written ahead of time. So the first one is this. This is the simplest Hello World program you will ever write. Even more simpler than the one that I have in the slides. So basically, like any other program, we need omp.h because that's where all of our OpenMP functions are. We need to include that before we do anything else with OpenMP. And now we get to our main function. So this main function doesn't even require any of that. So this is the simplest. I just made this function even simpler because it had some stuff in the parentheses that we weren't even gonna use. So it's just int main. So the next part that follows from that is this directive here. We are defining a parallel region as an area between curly brackets following the pragma line. So the area between the curly brackets following this line of code, this is a parallel section. This code, what happens behind the scenes is the program forks into however many threads this program can run with. How many threads? We'll get that in a bit. Basically, it's going to fork into some number of threads, and then every thread is going to execute the same code within the curly brackets here. If for whatever reason you exclude the curly brackets, then the parallel section is assumed to be the one line of code following that. So I'm going to put the curly brackets here just for the sake of demonstrating that the parallel region is defined by some area enclosed in curly brackets. So here, every thread is going to call the same printf line. It's going to say hello world from thread %d of %d. It's going to print out the thread number, and it's also going to print out the number of threads. So it's going to print out hello world from thread such and such from this many number of threads. After every thread has said their printf message, the program finishes, and then we reach the end of the program here. Let's run that. So, let me close this and open up another terminal. Open in terminal. Now I had this program pre-compiled already, but I'm gonna compile it again for for the sake of demonstration. So, that's a program. It's hello1.c. So, let me just... Okay, so here is the command to compile your program. gcc -g -wall -f openmp -o, and then the name of your executable file, and then the name of your source code file. That is how you compile your program. That is how you compile your C program that uses OpenMP. I press enter, and it's going to compile. I do /hello1, press enter, and unlike every time before where I typed in the command to execute a program and I forgot to specify the number of threads, the system basically defaulted to some number of threads. That number of threads is defined by however many logical processors are on your system's CPU. So, on my CPU, this is in Windows, by the way. That's why you see 2 taskbars, because this is a virtual machine. On my 8-core processor, there are 16 logical processors. So all 8 CPU cores are basically to the system pretending there are 2 CPU cores per CPU core. So 8 cores, 16 threads. 4 of those logical processors, and I'm gonna go into my VirtualBox settings over here. 4 of those are being used by the virtual machine itself. So it's obscured by my web camera, but if I just move it out of the way, you can see here that the number of processors that I allocated to this virtual machine is 4. So that's why when this program ran, it ran with 4 threads. So we have hello world from thread 0, hello world from thread 1, hello world from thread 2, and hello world from thread 3. And then we reach the end of the program. So we can write. So here's another thing we can do. We can modify this program to work with any number of threads, because the key thing about OpenMP, well, I guess the key thing about pthreads is that we can specify however many threads we want our program to run. And the same is true with OpenMP. We don't have to stick with the default. In fact, we can tell this program to compile. When we compile this program, we can basically tell it how many threads we want. And it's much the same thing as we did with pthreads and all. So, I have already written ahead of time another hello world program here. It's basically modified from before. Here, we add back that int argc character star argv. That is the setup for getting the number of threads to run this program with from the command line. So we're familiar with this thread function. Yeah, so we're hopefully familiar with this strtoll function that gets the number of threads as a command line argument and then parses that as an integer. When we get this thread count, we can go to this directive here and add num threads and in parentheses thread count. That is a compiler directive that tells the compiler, okay, so when this program runs, it's going to now specify a number of threads based on what we typed in as a command line argument. So much like before, it's gonna execute the hello world line here, but this time it is separated into its own function. So now every thread is gonna call hello, and every thread is gonna execute this function here. So it's much the same as before, except now we can specify however many threads we want. Let's try it out. So the compile command for that is gcc-g-wall -f openmp-o hello2.c. I press enter, and now I can /hello2, and now it's like faulted again. I do this every time to demonstrate you need to specify the number of threads you want this program to run with. So I'm gonna do that again, /hello2, and I'm gonna run it with 16 threads. So now we have hello world from thread 4 of 16, thread 7 of 16, thread 9 of 16, thread 11 of 16, and so on and so forth from all 16 threads. It works. So what's going on behind the scenes? Well, the next several slides explain what this program does. Yes, starting right here, it explains what it does. So, certain directives in C and C++ are preceded by the pragma keyword. Directives specified to OpenMP are preceded by pragma OMP. The very first thing that we have to do is to include the omp.h library, the same way we would include any other library. We have our main function set up so it accepts command line arguments. That's what argc and character star argv are for. Then we use the strtool function to parse the value that we want from our command line arguments into something that our program can use. In this case, it's our thread count. We are hopefully familiar with strtool by now. We pass in the argument we pass in the command line argument as the first argument. The second one can be just left as null. And the third one, that needs to be the base of our thing here. So it's in base 10, so you type in the number 10 here. Most of the program up to this point has been running on one thread, but once we hit that pragma OMP parallel directive, that's when the program forks into what is called a team of threads. So however many threads was specified by the variable thread count, it's going to have that one main thread fork into however many threads are specified by thread count. So now we have this team of threads, and they are all going to execute the same function here. That is the hello function here, which is defined down here. So all of those threads are now executing the same function. They're all saying hello world, and once each thread is done saying hello world, it's going to wait for all other threads to finish. When we enter this block of parallel code, there are no curly brackets here, but basically it is implied that at the end of this parallel section here, which is basically right after this line of code, hello, the existence of a barrier is implied. So we have an implicit barrier. Those threads that have finished running that hello world function wait at that barrier, and basically they wait for all other threads to finish executing the same function. Once every thread has arrived at the barrier, all of those threads in that team join back together with the main thread. As I said, when a program forks into multiple threads, that resulting group of threads is called a team. We have a master thread, and that is usually the thread with ID 0. And it's usually also the parent thread. So this parent/master thread forks into a bunch of threads that matches the specified thread count as specified by our command line argument. So we want our program to run with 16 threads. It's going to fork into a team of 16 threads. So we start with one thread, and then it's going to fork 15 more threads. Unlike P threads, here the main thread actually participates in this team of threads. So, as I also mentioned, at the end of executing this parallel block, we hit an implicit barrier. All of our threads wait here until all other threads have finished. Once they've all arrived at the barrier, we join back with the main/parent/master thread. So we enter our parallel section, we enter our parallel block, we fork into a bunch of threads, we do some parallel code, we stop at a barrier until all our threads have arrived at the barrier, we join back with the main thread. This is called the fork and join model. Oh, also another thing, this program, much like our example programs with P threads, there's still no error handling at all. So it is a good idea I would highly encourage you to try to write some error handling code. So if, for example, I write ./hello2 and I forget the number of threads, it won't result in a seg fault, but it'll just instead default to some default number of threads. Whatever that may be, you can hardcode that yourself or whatever you want. Basically, we want this code to be robust enough so we don't have to be inconvenienced by seg faults such as this. One more thing. Starting at pthreads, you have the option to now use Windows for your labs. There are a few steps to that as well. In fact, if you look at past versions of this video, for past versions of this class, you will see me using Visual Studio all throughout. Also, you can write these programs in C++, but I would advise not using stuff such as IOStream. I would advise against using IOStream because if you use that, you might get race conditions from that. So, for that reason, I would advise using printf instead. Okay, so say you start up a project in Visual Studio. Not to be confused with Visual Studio Code. You create a project in Visual Studio, it is a C++ project. And that's okay because we can use OpenMP with C++. You write your program, but that's not enough because we need to tell the project we need to use OpenMP for this. So you need to go under Project and go all the way down to Properties. You open up this configuration properties window because now we need to specify we want to use OpenMP. Go to configuration properties. Go to C/C++. Go to language and then find the little option here for OpenMP support. Set that to yes. Click OK. When you run your program, if you just click the little play button on the top of the taskbar, if you just click the little play button on the top of the Visual Studio window, it's not going to work because this program is set up because it's set up to expect command line arguments. It's set up to expect command line arguments from the terminal. So if you just ran it as is, you're going to get this, and this is the equivalent of seg faulting on the Linux virtual machine. Because this program is expecting a command line argument and we just ran it through the Windows debugger, we gave it no such argument and then it stopped running. Debug assertion failed. So we want to run it a different way. First, build your program by pressing Ctrl-Shift-P. Then in the Solution Explorer panel, right-click the solution itself and select Open Folder in File Explorer. When that window for File Explorer opens, you should see a .sln file. That is the solution file for the whole project. If you've pressed Ctrl-Shift-B, that built the program, and that built program should be within the debug folder that is at the same level as your solution file. Open that folder. Inside, you should see a .exe file. That is your compiled program. Type in PowerShell into the address bar of Windows Explorer. And now, you can just type in /the name of the program, .exe, followed by the number of threads you want to run your program with. So as I said, you have the option to use Visual Studio now, because Visual Studio knows what OpenMP is. You just have to tell it to turn on OpenMP. I'm just going to continue on using Linux here because, well, we're writing off the successes. Hopefully we're writing off of the successes that we've had with pthreads, and I just want to continue that momentum of using a Linux virtual machine, just for the sake of consistency. But once again, you have the option to use Visual Studio now. You can do this on a Windows machine now. The instructions, the code is more or less the same, except for the part where you have to compile it, because there are a few extra steps when it comes to Windows. For Linux, it's just as simple as typing in the command. Okay. I'm gonna stop the video here, and then we're gonna continue off with the rest of this PowerPoint slide. Okay, now let's continue on with our discussion on what we can do with OpenMP. So, as I mentioned earlier, it's a good idea to add some error checking code. When you compile an OpenMP program, if you compile a C program that has OpenMP directives and OpenMP isn't supported, the program will just be compiled and all OpenMP directives are just skipped. However, if you include OpenMP.h and you start to include OpenMP functions, then compiling the program might throw some errors because the system doesn't know what OpenMP.h is. Okay. Now, I did have to stop the recording for a good while because I wanted to make sure everything, and I mean everything, was working perfectly. So with that, let's now proceed to the next step. And that is, we're going to write a whole new program using OpenMP. And that is an implementation of what is called the trapezoidal rule in calculus. So the trapezoidal rule is a technique for approximating the value of a definite integral. Basically in calculus, or more specifically integral calculus, you have some area under a curve, and you want to find what that area is. We can approximate that by dividing that area into thin strips of the same width. And then we define how tall each strip is based on whatever value we use. So we can have the left corner of upper left hand corner of that rectangle touch the curve of the graph, or we can have it be the upper right hand corner. Doesn't matter either way, because when we take this sum of rectangular strips to the limit, then the errors that sum would start to shrink down to 0. And the same is true if instead of using rectangular strips, we use trapezoidal strips. So we have two corners of our rectangular strip be the endpoints. So we have two corners of our rectangular strip, now a trapezoidal strip. They are now along that curve of f of x. We define that area of the trapezoid to be based on whatever the left endpoint f of the left endpoint plus f of the right endpoint. We add those two heights together and then divide it by 2 to get the average height, and now we get a rectangular strip. And then we just sum all these rectangular strips together, and then we have an area for the integral, the area under a curve of a graph. So basically what we're doing now is implementing a function that would find the area under a graph. And we can use code that looks like this. So this code, it's a little bit dense, but here's what's going on. And there are some simplifications being done here that I do want to explain. So let's open up this thing here because I have the explanation down here. So the area under a the area of a trapezoid is basically, you have two height values and a width. We are averaging those two height variables so that we get the average height here. So this height is now, so this dashed line represents the average height of heights 1 and 2. We multiply that by the width of the trapezoid. So that area of the trapezoid is going to be the two heights averaged out, so h1 plus h2 all divided by 2 multiplied by w. So we can have the area for a trapezoid represented by this area formula. The area under a curve is going to be defined as an approximation where we sum the area of a whole bunch of trapezoids. So here, tall squiggly and small squiggly are just the two different heights of our trapezoid. those are defined by whatever f of x1 is. So this becomes tall squiggly, and f of x2 becomes small squiggly. So that's what these tall squiggly and small squigglies are. They are the heights of the trapezoid, where we take x1 and x2 as the endpoints of our trapezoid. We feed them into f of x, and then we get some outputs. So that's what those tall and small squigglies are in the summation of trapezoid areas. So what's going on in this code here is some simplifications. Everything is being multiplied by w, so we can just take w out. And now everything's being divided by 2, so we can make some simplifications. Basically, this tall squiggly plus small squiggly, we can separate that into the sum of 2 fractions. But here's the thing, tall squiggly and small squiggly, this small squiggly is actually the same thing as the next tall squiggly in the next trapezoid. And then small squiggly here is the same thing as the tall squiggly in the next trapezoid over. So really what you can do is group these squigglies so it's one squiggly, if that makes sense. So basically we are simplifying this a whole lot. So now we have start squiggly over 2. And then, because these 2's cancel out, because we're adding half squiggly and half squiggly, these 2's cancel out. So now we have start squiggly over 2 plus next squiggly plus next squiggly plus next squiggly plus next squiggly plus half of the end squiggly. And by squiggly I mean the heights of these trapezoids. So now we have the start and end points of our area, which is start squiggly over 2 and end squiggly over 2. Everything else in between, that is just something that we can program using a for loop. So we can just start with the start value of start squiggly over 2 plus end squiggly over 2. We add all these other squigglies, and then once we have that plus this summation here, which we can calculate using a for loop, we multiply everything by the width of every trapezoid. So we're simplifying a lot of code here. And that's what's going on in here. Confusingly, h in this context is actually the width of the trapezoid when I think of the height of the trapezoid as being f of a and f of b. F of a is actually tall squiggly and f of b is actually small squiggly in this illustration here. So it's a little bit confusing because I expected the heights to be tall squiggly and small squiggly, but really it's h. So that's what w is supposed to be here. It's a little bit flip-flopped from what I personally expected. But the point is, this code will find the area under a curve. What kind of curve? We haven't defined that yet, but for our purposes, we're just gonna define our curve as being this. We're gonna, for our purposes, define f of x to be x squared. So this is going to be the area, this is going to be the graph whose area we're going to define. We're going to find. So this is simple, a parabola graph. So we're going to find some area between some endpoint A and some other endpoint B. This is the area that we're finding. And we can approximate that using however many trapezoids we want. When doing this, when parallelizing a program, there are 4 basic steps. Partition the problem solution into tasks, identify communication channels between tasks, aggregate tasks into composite tasks, and then map composite tasks onto cores. With our OpenMP example here, there are 2 jobs here. Computing the areas of the trapezoids and then adding the areas of the trapezoids. Computing the areas of trapezoids doesn't need communication between threads, because if we divvy up the work of adding trapezoids such that this is actually a sub-sum, much like how we were working with the pi estimation program, if this area is actually a portion, if you imagine this area as being a portion of the full area, then this work, all this work here, can be done by one thread, and it doesn't even need to communicate with other threads, because this work is independent of whatever other work each other thread has. The only thing we do need to synchronize, however, is adding this sub area with the global area. So yeah, we assume that there are more trapezoids. Also, we assume that there are more trapezoids than threads, so we divide the work by assigning a contiguous block of trapezoids to each thread. So if there are like 1,000 trapezoids, we, for example, divide the number of trapezoids into 10 groups, and then we give out 10 groups of trapezoids to each thread, and they're all consecutive. So here's the code for our trapezoid program. It is from page 231 of the book, and even though I had already written it out here, I'm just gonna rewrite the whole thing again. So open in terminal. Yeah, I'm just gonna write it out again for the sake of demonstration. So we're gonna begin with include standard io.h, include standard lib.h, and finally include omp.h. Next, we need to include our function prototypes. So void trap, and we have to pass in quite a few things here. So double A, and A and B are our starting and ending endpoint. So double A, double B, and N, where N is the number of trapezoids, and double star global result P. And then we need the function for f of x. So we're gonna call it double f x. Well, actually no. The input for this is a double, and the output is also a double. Okay, so now we can get to work on writing the main function. So int main, let me just comment this. And now, main function, int argc, character star argv, with square brackets. Now I need to define some variables. That's gonna be double global result equals 0.0, double A comma B, int N, and finally int thread count. Now we're gonna need to get the thread count from the command line argument. So thread count equals strtold argv1 null 10. Optionally, what we could do is pass in A, B, and N as command line arguments. However, we're doing it a little bit differently. We're just scanning them as user inputs. So here's how we get that. Print f, enter A, B, and N. And then we're gonna do scan f. If you're doing this on Windows, you might need to use scanf_s instead. For a Unix system, I'm just using scanf. And then I'm gonna say %lf, %lf. So the user's gonna type in something that fits this format, and then the values of A, B, and N are gonna be extracted from that. So address A, address B, address N. Next, we added a parallel section of code. I'll just comment this. So here's a parallel section of code. So I'm going to say _ pragma parallel num threads thread count. And I want to drive the point home where we define our parallel section as being between curly brackets. So I'm going to put some curly brackets, and within that curly brackets, I'm going to type in trap A, B, N, and then the address of global result. There we go. Print out the area. So print F with N equals percent D with N equals percent D trapezoids, the estimated area of the integral. And I'll just end this line here. And then I'm gonna pass in N, and I'll continue that on the next line. Print F from endpoints percent F to percent F is percent F. End line, and then I'm gonna pass in A, B, and global result. Then I return 0. Okay, so now we get to define the trapezoid function itself. Okay, so that's defined on the next slide. Okay, so void trap double A, double B, and N, double star, global result P, and then I'm gonna define some variables, double H, X, Y, result, and then double local A, local B. We're defining an area under a curve between some two endpoints. But because we're dividing the number of strips between different threads, each thread is going to be doing the work between specific sets of trapezoids. So local A, local B, and I equals an I and local N, and then int my rank equals OMP get thread num, and int thread count equals OMP get num threads. The next thing we need to do is do a whole bunch of calculations. So confusingly, H is not the height of the trapezoids, but rather the width of the trapezoids. So H is going to be B minus A divided by N. So that's the width of one single trapezoid. Local N equals N divided by thread count. Local A equals A plus my rank times local N times H. Okay, so, and then local B is local A plus local B. No, local A plus local N times H. And then we calculate the result. Okay, so there's local A and B. They are the starting and end points of this thread's sub area of the area under the curve. So it's calculating some sub area of the curve, and now we have to calculate the result starting with the starting and end points as defined here. So if we go back to our picture here, all of this is being all this stuff here is being calculated with a for loop, but we need to calculate this and this first. And that's going to be the start of that's going to be the initial value of this trap function's my result. My result equals f of local A plus f of local B divided by 2.0. And now we get to do our for loop. So for in I equals 1, no, I equals 1, I is less than or equal to local n I plus plus x equals local A plus I times h. And then my result equals, rather plus equals f of x, where we just calculated x, and now we are passing that into our function for our area. And f is going to be our quadratic function, and we're finding the area under that curve's graph. Next, we are going to multiply everything by the width of each trapezoid. So my result equals my result times h. And the areas of every trapezoid. And then we have a critical section here. And that critical section is adding that thread's area to the global area. So, pragma OMP critical. So that is the directive for declaring a critical section. So unlike, say, p-threads, where you would need something like p-thread mutex lock and then p-thread mutex unlock, we declared this as our critical section, and that unlock and that lock and unlock functions are implied. So here we type in global result p plus equals my result, and that's it. Okay, finally we get to define f of x itself. So double f double x, and then finally return x times x, and that's it. So let's compile this program and let's see what we get. Let's compile this program again, and the command to compile it is gcc-g-roll-fopenmp-o, the name of the executable, so it's trap2, and then the name of the source code file, so that's trap2.c. Press enter, and there's a little bit of a thing here, so let me just go fix that up and make sure. That was an error on line 22. I guess that should have been format lf %lf expects argument of type double. Let me just double check that. Or maybe I can just cheat a little bit and just copy paste it from here. So whatever that was, I'll just copy that here and into here. So apparently it was %lf %d. Clear. There we go, it compiled. /trap2, and it's by default because I didn't specify the number of threads. I'm gonna try it again with 10 threads. Enter A, B, and N. I'm gonna say 0, 10, and 1,000 trapezoids. Press enter. With n equals 1,000 trapezoids, the estimated area of the integral from n points 0 to 10 is 337.18 whatever. If I did this with exactly 0, 10 trapezoids, then I have a horrible area of 720 units. So the idea is if I do this again with endpoints 0, 10, and a lot of trapezoids, I'll get a better and better and better area under the curve. So I guess it looks like it's converging on an area of 3, 3, 3. There we go. So our program is working. So I guess that's going to be your next assignment, where you're going to write out this program and then make a few changes to simplify the code. And one of the simplifications is we probably didn't even need that critical section. You'll see how. So before we get to that, let's look at the scope of these variables. The scope of a variable consists of the parts of a program in which the variable is used. With C and C++ programs, you may think of the scope as the region within curly brackets that a variable is found within. If this is for the body of a function, then we're looking at function-wide scope. If we declare, say, a global variable, then that has file-wide scope. With OpenMP, threads may have variables that only that thread can have access to, so that's private scope, or threads may have variables that other threads can access, that is shared scope. So, there is an alternative way to write our trap function. So instead of passing 4 arguments to the trap function, the 2 endpoints, the number of trapezoids, and the pointer to the global result, we pass everything but the pointer to the global result. So instead of trap double A, double B, and double N, and then a pointer to global result, we just have instead 3 variables, and we don't pass in that global result at all. We go back. So we change our trap function in the following way. Now, instead of 4 arguments, there are 3 arguments. There are only 3 arguments, and there is also no more critical section. Each thread calculates its part of the calculation in the form of its myResult variable. So now, there's no critical section anymore, because instead of adding to a global result, we're now returning the value of that local sum, so that it would eventually be added to the global sum. The main function is now going to have that critical block, that critical section. So let's implement those changes first to the function here. We're going to modify the trapezoid function so it only has 3 arguments being passed in, A, B, and N. So now we don't have a critical section in here. We are just returning my result. Okay, let's see what changes we need to do. So we need to redefine this function so that there are 3 things instead of 4. So trap A, B, N. Instead of A, B, N global result. Okay, so here are the changes that we are to do. Our trap function has the following changes. There are only 3 arguments. There is no more critical section in the trap function, and trap function returns my result. Each thread returns its part of the calculation in the form of its my result variable. The main function now needs some changes. Now, it's that has the parallel. Now it's this function that has it's this part of the program that now has the critical section. So now we have global result plus equals trap A, B, N. And this is now our critical section. So if we type in pragma OMP critical, now we have a critical section inside of our parallel section. Now this new program should work the same way. If I recompile this, I misspelled it. Okay, so here's the other thing. Because that thing is now returning a value, we need to modify our trap function so it returns not void, but double. So double trap, and double trap again, clear. And now it's hopefully gonna work. So we're gonna run this program with 10 threads. We're gonna run it so that it finds the area from endpoints 0, 10, and we're gonna do 10,000 trapezoids. And now we got 333. Same result as we did the last time. If I do it again with even more trapezoids, so from endpoints 0, 10, and a lot of trapezoids, now we get 333.333 whatever. So we now have the same result as before. Here's what I mean by we don't even need a critical section anymore. We're gonna implement what's called the reduction clause. Okay, so let's go here. So our trap function had some changes. It now returns a return value that is a double. We have the main program have a critical section within that parallel block. The main function now has its own critical section within its parallel block, but there's a problem. The call to the new trap function is a critical section, so only one thread can call it at a time. If we check the runtime of this, we'll find that it may run slower compared to a single thread. There is a way to fix this. Instead of having the result directly increment the global variable that is our result, we store it in a local variable, then increment the global result by that variable. This way, each thread can simultaneously call the trap function and only need to take turns when incrementing the global result. So that would look like this. So instead of global result plus equals trap, we'll just instead say double. My result equals 0.0. Say my result plus equals trap A, B, N. And we say global result plus equals not trap, but rather my result. This way, each thread can simultaneously call the trap function and only need to take turns when incrementing the global function. So every function is now able to call trap. Not one at a time, but they do need to add to the global result one at a time. So if we recompile this program again, and then run it with 10 threads, from 0, 10, and 10,000 trapezoids, we still get the same answer. Nice. But here's what I mean by we don't even need a critical section anymore. OpenMP has a cleaner way of doing this critical section stuff. We specify what is called a reduction variable. A reduction operator is an associative binary operation, and a reduction is a computation that repeatedly applies the same reduction operator to a sequence of operands to get the same result. All intermediate results are stored in the same variable. We call that the reduction variable. For example, if we have an array of integers and we're trying to add all the variables, if you have an array of integers and we want to add up every value, all the integers in that array of integers, our reduction operator is addition. We have a sum. That is the variable in which we want to store our sum. We are repeatedly applying addition to that sum, so it's sum plus equals AI. Sum is that reduction variable, and addition is a reduction operation. What OpenMP has is a reduction keyword. So let's try this out. So we have now a reduction keyword in here. OpenMP has a reduction keyword that we can use the following way. So basically now, we don't even need this block of code here. So I'm just gonna comment out that whole thing. And we're gonna define a reduction operation. So that new code is # pragma OMP parallel I'm gonna do a backslash here that indicates that the pragma line is extending to the next line. And we say reduction, and then parentheses, plus, colon, global result. And then, on the next line, we say global result plus equals trap A, B, N. And there we go. These 3 lines of code do the same exact thing as these lines of code. And it's basically a cleaner way of doing things. So, if we try these changes now, I'm going to recompile the program once more, and I'm going to run it with 10 threads. I'm going to find the area under the curve from endpoints 0 to 10, and with 10,000 trapezoids, and now we get the same result as before. 33 dot whatever. So, yeah, OpenMP basically makes a lot of things easier for us when it comes to writing parallel code. Instead of specifying critical sections and then specifying critical sections, we just simply define one big reduction operation. And that's pretty neat, isn't it? These 3 lines of code do the same thing as these, 6 lines of code? 6 or 7 lines of code? Yeah. So we basically condensed everything into just one single reduction operation, and all we needed to do was add a few directives and a few functions, and that's it. This is basically a much faster way of writing parallel programs. And when it comes to writing parallel programs, the one thing that you may want is to write your code faster. Conveniences that make it easier to write code. There are a few caveats that I do want to talk about, however. But I guess I'll get to that in a little bit. Okay, so the syntax of the reduction clause is as follows. Reduction, left parenthesis, operator, colon, variables. So reduction operations include addition, subtraction, multiplication, bitwise and, or, and exclusive or, and also logical and logical or. If your reduction variable is a floating point variable, your result may actually differ because floating point arithmetic isn't associative for complicated reasons. So the result of if your reduction variable is a floating point variable, your result may differ based on the number of threads used, and that is because floating point arithmetic is not associative. There is an even faster way. There is another way to parallelize our whole thing. There's another way to parallelize our trapezoidal rule program using the parallel for directive. So here's the program used before adding parallel for, and there it is now. So with a parallel for, basically with a parallel for, instead of having the basically we're combining our reduction operation, and now instead of having the parallel section be part of the main function, it is now part of the trap function. So here's the modifications we do for that. Basically, in this version of the program, which I might have to do so in a different separate video because this is getting long and I have to get to class right now. I'm sorry if this feels a bit rushed. I might have to do this in 2 parts, basically. Instead of having double A, double B, and double N, and then using those to calculate, instead of having this be called by every single function, we call it once, and then all the parallel operations are within the trap function. So there is no more local A, local B, and local N. We are parallelizing the whole for loop by using a parallel for directive. So I think I'm gonna have to cut it off here, and then in the next video we're gonna look at using parallel 4. So I think I'm gonna have to truncate this set of slides, simply because there's so much I need to get to talking about, but I don't have enough time for it. So my apologies that this feels a bit rushed. So I think your next assignment is to do everything up until using parallel 4. So your next assignment will likely be to write a parallel Hello World program, and then writing the trapezoidal rule program step by step, making changes along the way until we get it working. And then I guess in the next video we're gonna implement the parallel 4 directive, so that way when we write our parallel program, we don't have a parallel section in which the function is being called by each thread. We call the thread, and then inside that, no, we call the function, and within that function it's parallelized. So we call the function once instead of calling the function multiple times. So that's gonna be interesting. So I think I'm gonna have to cut it off here. So my apologies if I was rushing, because I guess I was rushing. So I might have to continue this starting at the parallel 4 directive here. So yeah, we're gonna have to stop at the reduction clause and continue in the next video at this point. So that's gonna be your next assignment. You're gonna write a hello world function, and then you're gonna write the trap function, the trapezoidal rule program, in various ways, making changes along the way until we get to the point where we implement our reduction function, our reduction operation. So with that, I'm going to post this video sometime tonight because I really am in a rush. I really am in a rush, and then I'm gonna have to post the next assignment later tonight as well. So with that, I'm going to end it here, and then next video we're gonna continue off with the parallel 4 directive. Alright, I'm gonna end it here, and take care, and hopefully you should see the next assignment later tonight, and yeah, we'll go from there. Alright, thank you, and have a good day.